Yeah, so I'll go ahead and start on the logistics stuff. So logistics-wise, we're going to run everything through GitHub. So I'm going to post lecture notes and stuff on here. We're recording lectures. Hopefully that's okay with everybody. But just so like if people miss or like want to join in the middle of the semester, they can go back and watch things. That's also accessible through GitHub. I wrote out the syllabus, which we're going to try to stick to as best as possible. The main thing is this is really going to be like what you get out of this seminar is what you put into it, because it's going to be student run, and most of the time hopefully it won't be me up here lecturing. It'll be, if everybody does the reading, we can hopefully take turns having like other people lecture. I'm prepared to lecture the whole time if nobody wants to do that, but I would rather not because I have other things going on. So the way this will work is I'll send out the reading because I have it kind of planned out in Artin, which will be our reference text until about February. And what we're going to do is everybody does the reading, and one person like emails me 2 weeks in advance is like, hey, I want to lecture on this Monday on like this material. And then that way you have like 2 weeks to prep your notes, and we can post the notes to GitHub. And then that way everybody can reference your notes and your lectures on YouTube and like stuff like that. So it's really just like a group thing where we're all learning the stuff together. There are some people in here who have taken 430. There are some who have taken 431. There are some who have taken neither. So we're starting at 430, which is abstract algebra 1. In some ways, this is ideal. In some ways, this is less ideal. For those of you who get the joke, laugh. For those of you who don't, we'll see you in 2 months. But no, yeah. Going through this, once we get through the content in Artin that I want to get through, I've mapped out 24 lectures, which should take us until February. Just saw it convertized. Yeah, this took me like 3 hours. Once we get through these 24 lectures, we will have covered mostly ring theory, some module theory, and a little bit of field theory, but we're skipping out on Galois theory. If you want to take Galois theory, take 431, it's just not pertinent to algebraic geometry. Once we finish that, we're going to go into Hartshorne chapter 1, and then we're only going to use Hartshorne chapter 1, and we're going to change textbooks and use Wiki, because that's kind of the popular book right now in grad schools. So who should take this seminar? People who have taken linear algebra and want to know more about algebra in general, and maybe algebraic geometry if you know anything about it, and if not, I promise you it's cool. Who should not take this seminar? Nobody, unless you don't know anything about matrices, because they will be our prime example for the first like 8 weeks of this. That's all I really have on logistics. So yeah, check out YouTube if you miss a day or something. Okay. So today's schedule is a little bit rushed. I'm trying to get through all of the main definitions from 430 that a lot of people are familiar with, and then use reference texts for the rest of it. I have back chalk. So today we'll be talking about permutations. Hey, Dr. Jones. Permutations of the standard basis as a way to talk about permutation groups. We'll talk about function composition and associativity. We'll define what a group is. We use the symmetric group as our prime example of it. We'll talk about subgroups, a little lemma about what makes something a subgroup if it's finite. Our primary example here will be BZ, which we'll talk about then. We'll briefly discuss the Euclidean algorithm. Qth roots of unity is another example of a group. We'll define the order of a group. We'll talk about group isomorphisms, this thing called conjugation, group homomorphisms, the image and kernel of a homomorphism, and then we'll end with some examples about homomorphisms. So for those of you who have taken 430, this is hopefully familiar. For those of you who haven't, don't need to worry. I promise this is reasonable. Okay, so starting off, if we're going going to define an arbitrary vector space V with coefficients in some field, in this case R, of dimension n, then we can talk essentially about the matrices of size n by n, which are square matrices. Assuming everybody here has taken linear algebra, you'll recall that the standard basis for a matrix of size n looks like E1 with n minus 1 zeros, E2 really I'll put this as n. As 0 is going down into the last slide. And so, as it turns out, when we want to think about permuting a list of n things, all we have to do is have a block matrix composed of these vectors, where it's some permutation of the EIs in this middle, and then we'll multiply in our list of things that we want to permute around. And so one such example, we could do, hey Josh, there's some logistics stuff in the first few minutes. Recording will be posted on YouTube, so just go ahead and do that. So in the vector space of real matrices of dimension 3, we can talk about some explicit permutations like so, which maybe an easier way that we'll write this in the future is E2, E1. And so when we talk about these permutation matrices, it's a nominal idea to just put in something over here, multiply it through, and see what we get out as a column vector. And so here we'll get in the first slot B, in the second slot A, and in the third slot C. Now, the way that we kind of want to think about this is that these matrices are invertible, for sure, and that actually their inverse is their transpose. Another word for these that Artin uses in the book are called elementary matrices. So elementary matrices are invertible, and an elementary matrix E, its inverse is E transpose. So one such example is that if this is E, then E transpose becomes, I think, actually just the same thing. Yeah. Right? So E transpose here is the same thing because this is a transposition, right? That leads me to my second point. So a transposition is a special type of permutation which flips explicitly two rows of the matrix, or two rows of this column vector here. And so this will be a permutation in terms of matrices is action which switches 3 or more rows. Transposition switches exactly 2 rows. And so the first big theorem in Artin in this section, as you guys do the reading, is that all permutation matrices are composed of transpositions. We will later show that this holds for more than just permutation matrices, but rather for permutations themselves. And we're going to prove this in section 2.1 in the context of the symmetric group, and then I will leave it as an exercise to you all to go and backtrack that through if you care about this in particular. So this is kind of how Artin starts off the book, and I'm trying pretty closely to follow his train of thought here, because he's smarter than I am. But we're going to go into function composition, we're going to define a group, and then we're going to talk about a special type of group that acts a lot like permutation matrices. And then we're going to show that the two things are structurally equivalent. That you can think of permuting colored chalk on the desk here the same way as you can think of permuting entries, row entries in a column vector with permutation matrices. And then later as an exercise we'll show that the combination of permutation matrices is closed, that you always get another permutation matrix out. Okay, I'm going to make sure I didn't miss anything. The sign of a permutation in Artin, this is just important if you're reading through it, is the determinant of the matrix, and that's always plus or minus 1. Hopefully that is a fairly clear thing. Okay, so we define, and here I want to use his exact notation so that I don't use different notation in the book. We'll say that F is a law of composition on set S such that F from S cross S to S is essentially associated. And really our primary example here is if we take away F, or maybe you'll have seen this from earlier today, and we literally just use function composition, this is really what we're talking about. But in the more abstract sense, people like to use other symbols for it besides \circ. And so we'll be thinking of this sometimes as a morphism of a certain category or something like that. Yeah, in terms of associativity, when we're talking about groups, unless we're talking about explicitly the group Z+, I'm going to use multiplication notation. Mostly because addition implies commutativity in a lot of ways, right? So 3 plus 4 is equal to 4 plus 3 kind of seems to come naturally out of the way it's written. 3 times 4 is a little bit less natural for commutativity, and so we use multiplication to denote ambiguity about whether or not something is commutative. So as we're thinking about function composition, I guess I'll put this as a remark because I'm not really sure what to put it as. Let me add a backup definition here. So we're going to call more T to T is a set of, we'll say functions for now, and later it'll mean morphisms. T itself. So such examples are called automorphisms, so permutations are a prime example of this. But our remark about associativity is that function composition really is associative because if you have a sequence, without defining too much of category theory to slow this down, if we have a set of maps, F, G, and H from T to T to T to T, then we also have attributed maps that are compositions of these things, right? So if we go from F to T, and then from T to T by G, this is equivalent to F. And then similarly, if we go from the second T to T up here, this is equivalent to H sort of G. And then to really define associativity, we have one more big leap, which is, of course, F sort G sort H, or very alternatively, H sort G sort F. And so my claim is that this diagram commutes. I don't think we need to prove that. I think we're willing to take a function composition as associative at face value, and that all these things so the easiest way to see this, and the way that Artin presents this, is by a multiplication table. And so people who have taken 430 with Dr. Jones will have seen this in one way. This is a slightly different presentation than what he does. So consider a set with two elements. Then there are really four and if this is T, then there are really four maps on this set. And rather four maps in more TT. One is I, which is the identity map. So I of A is equal to A, and then I of B is equal to B. The second map is the transposition map, which we'll call tau. And tau is defined by tau of A is equal to B. Tau of B is equal to A. Again, this is kind of like the idea that we had with permutations and transpositions. We're switching two elements. And then the constant function. And there's a constant function for each. That alpha of B is equal to alpha of A is equal to A. And beta of B is equal to beta of A. Artin goes through, and because I'm expecting people to do some reading here, it's figure 1.3, and he basically shows that you can view this as a multiplication table where it's one composed with the other creates something else. So if we were to compose the constant function with the transposition function, we're always going to get B. But if we start with the transposition function and we move to the constant function, we always get the constant. Yeah.
So in general, when the size of T is n, there are n to the n mappings, right?
Wait, say that one more time?
If the size of T is n, if there are n things in T, there are n to the n mappings.
I think it's just n squared.
It's n to the n.
Okay. I honestly, I don't know. I'm not entirely sure. And then, okay. I trust Connor. Yeah. So we're going to make another definition, which is that we'll call it identity element of the objects of something that we're working with, and we'll let let me just shut this. We'll let the object of this thing that we're working in remain androgynous. Hopefully that's okay. We'll say that in a set S with an action on it, such as circ or anything else, we can have a function which is an identity. And we'll usually call that function E. And so it's not quite a definition, so I'm going to put this as notation. E in S is the identity element under function composition, where for every A in S, EA is equal to AE is equal to. Similarly, we can have, and this is more of a definition, A and S is called the invertible element if and only if there exists B in S with AB is equal to BA is equal to the identity. So this is where we build up to our big thing. So G is a pairing on a set. S is a binary operation times is a group if and only if one closure, which is that for all A and B in G, the product AB is also in G. Associativity for all A, B, and C in G, A product B product C is equal to A product B product C. Identity, which is there exists E and G is defined above, and then inverses. Every element of G is invertible. Here I'm just going to call it A inverse because I think we're all clear with that notation. Some examples of groups. And here it's worth clearing off some before. So the first one is going to be real numbers under addition. And so this is a group because we have 0. We have, for any real number, some additive inverse that takes us back to 0. We're closed. We're not multiplying in anything that gets us, or not multiplying. We're closed. We're not adding two things and getting something that isn't a real number. And then we have associativity just by the way we define multiplication on numbers in general. So I'm not even actually going to write it here. Another one, just as easily, could be real times. And this one requires a little bit more because to get invertibility, this is kind of the thing that we don't get with Z. So Z under multiplication does not form a group because you can't divide by integers unless you have some other weird thing that we're going to talk about probably next time. Yes?
We got to kick 0 out, right?
Yeah.
For multiplicative inverses.
Well, we got to kick 0 out for multiplicative inverses unless we do another funny little trick that we will talk about next time. And that's really just specifically modding out by a prime. But yeah, so with our times, the trick here is just that we can divide by numbers. We have multiplicative inverses, except for 0, which we just kind of let be special. The really important one that we focused on at the start or permutation matrices, and specifically the symmetric group of n elements. So for n things, we can permute these a bunch of different ways. And it turns out that the structure of that thing is the same as what we were looking at the start of this lecture with permutation matrices. We will examine for tonight mostly S3. And I think, yeah, and then, okay, the other one that Artin uses is GLN over R, which is the set of all matrices A in n by n matrices with determinant A not 0. This is the general linear group of matrices. Yeah. Yeah, so let's work through classifying the group of order 3. So S3, and I'm going to introduce something here that will show up later tonight. And so essentially I want to think of all of the permutations of 3 elements like a triangle. And what we're going to do is we're going to say we can rotate this triangle and we can flip anything by fixing one element. And that is structurally the same as doing our thing as either transpositions or rotation matrices. And we will make that clear in a little bit. So essentially, we can rotate everything once, which means 2, we'll just rotate clockwise. 2, 1, 3. And then 1. We can leave it the same. That's not going to be a triangle if I can draw that. Or we can flip elements. So if we fix 1, let's say, and we flip 2 and 3, or if we fix if we fix 2 and we flip 1, nope, we fix 3, we flip 1 and 2. Or if we fix 3 for real this time and flip 1 and 2. We can denote in this way exactly 3 factorial movements. And so, I guess just continuity here. That this is very clearly our identity function. This leaves everything the same. This we're going to denote by sigma with a subscript of the thing that we flip, or sorry, of the thing that we fix. So this will be sigma 1. Here we're fixing
Fixing 3.
Fixing 3. And then here we are fixing we should be fixing 2 here. And since 2 is in the bottom left corner. Alternatively here, we are rotating things. And so the rotation elements are tau 1, meaning we rotate it once, or if we were to jump all the way over here, we rotate twice, and we get tau 2. So the group of function composition on 3 elements is defined by all of the ways that we can rotate essentially this triangle. Yeah?
The way that the arrows are, for tau 2, shouldn't the arrow start at the enemy?
Yeah, it really should. Yeah, because that's basically just the same thing as tau 1. Okay. Now, hopefully it's clear. Obviously, the initiated know this, but for the uninitiated, doing this 3 times gets you the identity. So we have something that is cyclic of order 3. It cycles around every 3 times you do it. And then here we have something that is cyclic of order 2. It cycles around every other time you do it. You flip 2 rows in a matrix, you get the same matrix back after doing it twice. It's worth noting, when we said earlier that we had the theorem that all permutations are construction of transpositions, combining any 2 of these transpositions, the sigmas, that are disjoint, any 2 distinct sigmas gives you a rotation of some kind. Play around with this on your own if you haven't seen it. If you've seen it, you might be a little bored. So you can also think of this, of course, just as like a list of things, right? So if you have 1, 2, 3 getting sent down to 1, 2, 3, and that's your identity map. If you have 1, 2, 3 getting sent down to 2, 1, 3, well, we're fixing 3. That's pretty clearly sigma 3. If you have sigma 2, well then 1, 2, 3, we can fix 2. Swap this. I will add little invisible lines here because these things are not going to do that. But 1, 2, 3, fixing 1. Same thing here if we wanted to do tau 1, 1, 2, 3, we rotate everything around once. 3, 1, 2. Tau 2. 1, 2, 3, we move everything twice, and we end up with 2, 3, 1. And hopefully it's clear that even though we wrote it 2 different ways, these 2 things have the same structure of function composition. Since we have people who are in 430 or haven't taken 430, I'm really emphasizing the idea that the structure is the same no matter how we choose to write it. Okay. So now I want to very briefly talk, even though we're going to talk at length about it, before I go on. Any questions? Okay. So, and I'll maybe leave the definition. So, a subgroup of a group is just a subset of the set that happens to also be a group. And there's a long way to characterize it. Okay, if I look on Gunner's face, I should take the long way to characterize it. So, H, and okay, here's the part, notation. The less than or equal to sign no longer means less than or equal to, unless I say it does. Now it means subgroup. So there you go, but this is common notation, I swear. H is a subgroup of G if and only if H is a subset of G which happens to be a group. However, I'm going to point out some nice things that we get out of the structure of taking a subset of a group. For one, associativity is free. If you have an associative product on a set, it doesn't stop being associative because you shrink the set down. So we don't have to worry about proving associativity to show that something is a subgroup. So that's not even really worth a theorem, but I'm just going to say lemma, don't need to prove associativity with 2 S's, not 3. Okay. Theorem. If G is finite, we actually only need group. And so the proof sketch is that we can pick some element of G, and because it's finite, I'm using some number theory that we're going to define in a second, so we'll come back to the sketch. But because G is finite, it has to circle around if we exponentiate this element. Keep in mind, exponentiate here, we can just use the same notation that we've always used for exponentials. A to the n means just concatenate this thing n times. And so essentially, because it's finite, it forces it to cycle around. Yeah?
For that lemma up there, we also don't need to prove that the identity necessarily is in the subgroup, because if we have closure and inverses for every element,
Yeah.
then we must have the identity.
Yeah, I mean, like, if you have inverses, then that's fine, but I'm just starting from the top of, like, yeah. Yeah. If you have associativity, or no, you don't need to prove associativity. If you have inverses, you have identities. Okay. Yeah. Artin makes a definition here that he uses for a bunch of examples and to specifically motivate some number theory. So BZ is the set of all B times little z, z, I guess really it's just BZ such that and this is important later. When we talk about cosets next time, this is going to be our first example of a coset. But yeah, I mean, so this is basically just multiplying through the integers. So for example, holy, that does not look like a 2z. Is like -4, -2, 0, 2, 4 in all directions. 2z is a subgroup of z under addition, z plus. It's not finite. I don't feel like proving it. You should go through it on your own if you haven't proved something as a subgroup before. Text me if you need help with that. What this motivates, though, is that if you have BZ, and this is actually really theorem. AZ plus BZ can be turned into DZ, where D is the greatest common divisor of A and B. And this is where really Artin tacks on number theory as like a side thought and says, hopefully you've seen this somewhere else. Hopefully you've all seen this somewhere else. Has anybody not seen the division algorithm somewhere? Awesome. Okay. That is like the best thing ever. Okay. So given that you all know the division algorithm, do you know the Euclidean algorithm for finding the GCD? Okay. Everybody? All right. Then actually that just saves us a bunch of time. Essentially, and we'll go into some more number theory on this later for when we're talking about torsion groups and Z modules in like 2 months. When we're talking about torsion groups and Z modules, we'll end up using this for like quotient groups that are not B. So anyway, that's awesome. Yeah. Quick definition. I guess, so one other example are called Qth roots of unity. I don't think we're kind of running out of time right now. We have 20 minutes left, so I want to skip Qth roots of unity. We'll talk about the order of a group real fast. The order of a group is the number of things in it. So we denote it by bars G. Is really just the number of things in the group. Number of elements of G. And this is important when we talk about Cauchy's theorem, Lagrange's theorem next week. Yeah, it's in 2 lectures that we're going to talk about this more. There's two examples that you should read about on your own if you haven't seen them before. Page 48 in the first edition of Artin, the Klein 4 group, or the Veer group, is kind of interesting. And then the quaternion group can be interesting if you haven't seen quaternions before. Both are kind of neat examples of groups, and then they're neat examples of groups which are not cyclic. And so realizing just now that I did not define cyclic. G is a cyclic group if there exists an element little g in G such that G is equal to parens G is what we're going to use here because the Langle and Wrangle have meaning later on. But it's equal to all of e to the I such that 0 is less than or equal to I is less than or equal to n, where the order of G is n. So some examples of this. Z mod 6 under addition is a cyclic group because you can add 1 to itself 6 times and get all of the elements of the group. Certain matrix groups are cyclic. I think the group of over triangular matrices is cyclic under multiplication. I don't know. If somebody knew, then that would be confirmation, but nobody knows, then look it up later. Okay, so remember how we talked about the idea of structural equivalence between the triangle with 1, 2, and 3 on it, and then the other way that we ended up writing, it's called two-line notation. It's like dropping down the 1, 2, and 3. The structural equivalence is something that we really end up caring about a lot in abstract algebra, and then later on in algebraic geometry. A lot of the idea of algebraic geometry is trying to classify these things called varieties and compare them to each other. And when we want them to really be the same, but they just aren't, we have this other type of thing called birational equivalence that acts like structural equivalence, minus finitely many points that we don't like. But for groups, we don't really have that. And so we need this thing called isomorphism. And Artin talks about isomorphism first. I think all of our 430 classes at JMU talk about homomorphism first. No?
No, friendly introduction to abstract algebra, but Dr. Artin too.
And it did isomorphism first?
Yeah.
Really? Okay.
Because isomorphism is so strong that it has so few properties compared to homomorphism.
Yeah, that's true.
So they're just like, it's isomorphism. Anyway, going to homomorphism.
Yeah. Okay, so let G and G prime be groups. We say, and I guess let phi from G to G prime be a bijection. Everybody knows what a bijection is? Okay. Side definition. So f from A to B is injective. I'll make this a lowercase f for addition. If f of B1 equals f of B2 implies that B1 is equal to B2. So it's basically saying if you have two things that are the same in B, then they have to have the same preimage. Another word for that is fiber. We'll use preimage and fiber interchangeably, but we'll usually use fiber to mean like the fiber of a point versus the preimage of a set. They all just mean the thing from before the function. Similarly, f from A to B is surjective if for every B and B, I realize I maybe shouldn't have used B's in here. They're elements of A, I promise. If for every B and B, there exists A in A, if F of A is equal to B. Finally, F is bijective if and only if it is injective and surjective. So what it gives you is this one-to-one correspondence that's guaranteed to hit everything in the image of a function. Now, if we have a bijection between two groups, we call phi an isomorphism, and really a group isomorphism, if and only if for every A and B in G, phi of AB is equal to phi of A product phi of B. And what I'll really emphasize here is that if we have this product, this is the product in G. Whereas this is the product in G prime. And so what we are preserving, we have all of the elements have a one-to-one mapping with each other, and all of the elements in the image of a function get hit. And then we also have that our product on the set, the thing that gives the group its structure, kind of like function composition, is preserved through this map. In topology, this is just our definition of a continuous map. It's just this. A homomorphism is a bijection that goes both ways, so it's error reversal equivalence, but more on that later. Yeah, so this is an isomorphism. One such example is the dihedral group of order 6, the triangle, is isomorphic to S3, the symmetric group of 3 elements. That proof basically involves a visual mapping, so it's maybe not ideal. But we can talk about like permutation matrices of order 3. Well, if we wanted to write down all the matrices, we have the identity matrix, that's E. And then we also have our transpositions, where you just fix one column. So like E1 fixed in the first column, E2 fixed in the second column, E3 fixed in the third column, gives you all of the permutation, or all the transposition matrices. And then the rotation matrices are the composition of the rotations, or you can just move around every single column. So by moving every single column, you get permutations. That has an isomorphism to S3. This is the basis generally of representation theory, which we'll talk about in 2 weeks. So, a calmer idea of the isomorphism is very similar and takes this specific line. So keeping the G and G prime, phi from G to G prime is a homomorphism if and only if for all AB in G, phi of AB is equal to phi of A, phi of B, the same way it was here. The difference is that phi is no longer a bijection. So we do not have this kind of one-to-one correspondence with surjectivity. This is kind of a remark. I think Artin has it as a theorem, but homomorphisms preserve the identity, and then they also preserve the thing that acts like 1. So if it's a cyclic group, it preserves 1, the smallest thing that generates the group. And if it's a combination of cyclic groups, which is not inherently cyclic, but can be broken down into its torsions, then it preserves all the different units. So I have 8 minutes right now. I want to talk about two things: the image and kernel of a homomorphism, and then I want to maybe hit one important example, and then the rest you can read about in Artin between now and whenever you feel like it. Yes.
The kernel's the same thing as the null space, right?
Yes. And actually, that is a very good connection, because that shows up in a different way in algebraic geometry. Okay. Keeping homomorphisms up here, remembering that isomorphisms are just bijective homomorphisms between groups. We define the image, I guess I should really put, sorry, using the same notation as before, phi from G to G prime, the image of phi is equal to all of the G in G prime, such that there exists A in G where phi of A is equal to, it's all of the things that get hit. G, we have G prime, then maybe some small subset over here is the image of phi, and everything lands in the image of phi, but it's not all of G prime. Similarly, the kernel of phi is the set of, all keeping it consistent, A and G, such that phi of A is equal to 0. And so really, maybe we have cur phi over here. It's really, and I'm going to use a different color for this. So all of the stuff that gets sent to 0 in the image of phi. Notably, 0 is always a subset of the image of phi, and the kernel is in sort of the range. I guess, yeah, it's in the range. So these are the last two big definitions. Are there any questions about these? I think 4 of you have seen this. Yeah.
So by 0, you mean the identity in G prime?
Yeah, that's, okay, I'm really glad you said that now. When we're talking about rings, we're going to use 0, because it just exists. But yeah. In this case, it'll be the identity. When we are talking about rings, it'll be 0, not 1, because we'll have 2 different identities going on. But only worry about that if you know what I'm talking about. Okay, so examples in the last 5 minutes of homomorphisms. So over here, I have them written out. The determinant from the general linear groups to the real numbers under multiplication is a homomorphism. So the general linear group means that we can combine matrices with matrix multiplication. And then it just happens to be a byproduct that you can prove that we never end up getting to determinant 0 under matrix multiplication. And so, because we never get that determinant 0 thing, the determinant is always not 0. And so it sends something to R under multiplication. I do not think that that's an isomorphism. I don't think. Is the determinant from the general linear group to R under multiplication an isomorphism? I don't think so.
Because you have like multiple elements
No.
that have the same determinant.
Yeah, that's exactly it. And then, yeah, so then the inclusion map is just from a subset of a group to the group itself, and it just preserves the subgroup. So if you have a subgroup of G, H, you just preserve all of H inside of G. That's a homomorphism, and it doesn't hit all of G. And that's actually the exact picture that we have here. So this is basically the inclusion map. Then there's the projection map. One example is just Z plus going down to ZP, where P is any integer because we're under addition. And this just takes an equivalence class, which we'll talk about next time. But I think most of you have seen equivalence classes of Mod P. So all of these three things are examples of group homomorphisms. We'll talk later on more abstractly about morphisms, but for now, when we say morphism, we mean group homomorphism, unless we say this. Okay, that's all I've got for you. Next time, we'll talk about equivalence relations, cosets, restrictions of homomorphisms to subgroups, and then we'll talk about products of group objects and fiber products of group objects. That'll be kind of our first little hint in category theory, and the first time that like we'll really hit something new